So I'm going to speak about curiosity, about theories of curiosity, to try to understand better curiosity in humans, how we can experiment those theories to see whether they're right or not, and how we can apply them to educational settings. But first, let me start by observing that we live in a world that is changing extremely fast for many reasons. For example, the climate is evolving very fast. The geopolitical situation is changing fast. And there are technologies that are now changing everything. And that not even scientists could predict would arrive 5 years ago, such as artificial intelligence. And yet, in this fast-changing world, if we look at school from a bird's-eye point of view, really it's more or less the same school in many countries as the school that was there 50 years ago. What I mean is that it's still, in most cases, there are many exceptions, of course, you can always find exceptions, but if you look at the big picture, it's still really the same disciplines that are taught in the school than 50 years ago. And it's still very much teaching that is top-down, like knowledge going from the teacher to the kids in a very descendant manner. And maybe it has been working at some point in the past, but today what we observe is that the skills in the mathematics, in reading, the basic skills are decreasing. And this is in spite of actually the budget of education going higher in a number of countries. So we need to understand what we can do and what's happening. So let me focus among those revolutions to say a few words on the AI revolution and why I believe it's pushing particular societal and educational challenges. So the revolution we are talking about is not about AI in general, but more specifically due to the advent of generative AI 3-4 years ago, which just in a few months got 100 million users in the world, and now you have 3 billion users every month of only ChatGPT, and there are so many other systems. And so those systems, there are many ways to view them. One thing that's very important to have in mind is that they can produce text or images or videos that might have been produced by humans, and just in a few months we will be able to see full movies, entire movies, several hours long, for which it will be completely impossible to guess whether they were produced by a team of humans or machines. And we need to prepare already to be in a world where we will be surrounded by text, images, and videos, which majority of which will have been generated by AI, and for which it will be completely impossible by any technical way to know whether it was generated by AI or not. So it is changing the world picture a lot. The adoption rate is extremely fast. It's not so fast in populations over 35 years old, but for the young population, it's extremely fast. We've been doing a number of statistics in France. Well, when I say we, not only the lab in which I work, but various institutes. And what we've been observing is that vast majority of the younger people, the ones who are still at high school, are using those techniques. And this is rising even more in middle school. And what we have been observing a lot is that quite often kids start using generative AI as a way to do homework a little bit quicker than they should. But then very quickly they tend to use generative AI for anything that's related to accessing information. They want to buy a new piece of sports suits, they ask ChatGPT. They want to know about what's happening in Ukraine, they ask ChatGPT. Whatever they ask, they don't use anymore search engines. They don't use anymore, well, they've stopped using anymore, but for a long time, the press, the official press, whether it's online or on paper. So let me highlight among the many societal stakes of AI, 3 of them. I know there are others which are extremely important, for example, environment, which I will not discuss today. So one important societal stake is for democracy. One very important way of viewing generative AI is to view it as a cultural transmission technology. So what do I mean by this? What I mean is that the way to build a Gen AI system is by building a corpus of text, of images, of videos, and use algorithms that detect regularities in those texts. And those regularities, they basically encode basically the values, the knowledge, the beliefs, the myth, the preferences, the biases that are present in the corpus of text, and which basically represent the diversity, or not so diverse, sometimes cultures in the text corpora. And so what this means is that if you, in the end, discuss with a Gen AI system that was made by Americans or Europeans or Chinese, for many, many topics, they will not propose the same vision of the world. So, for example, just try to ask what happened on the Tiananmen events in China to DeepSeek. It will not answer you the same thing as if you ask to Mistral, for example. And that's very important to have this in mind, because what I said 2 minutes ago is that now kids are using those tools as a way to access information and knowledge about the world. And it means that they will be exposed and biased by the particular vision of the world that is conveyed by those models. And even if some people realize that Gen AI is a cultural transmission technology and they don't want their brains hacked and influenced by those techniques, they can't escape. And they can't escape because simply the vast majority of text that will be available and videos and images that will be available around us will have been generated by AI. So even if you don't use AI, you read AI. And finally, for a number of years, the world has been changed also by social networks. And now there is a good cocktail of the mix between social networks and AI, where very small organizations and even single individuals now can deploy millions of bots in a few hours to influence what people think about any topic, whether it's about wanting to sell a product in an economic context or whether it's about influencing the election in a democratic country. And so this is why this is having a major impact on democracy right now, and it's impossible to think we should not educate children about those issues. There are not only challenges, there are also opportunities which are extraordinary. In the sciences, for example, those techniques are profoundly changing the way scientists do science. And they are already leading to extraordinary discoveries. This was marked last year by giving the Nobel Prize in chemistry and in physics to researchers in AI. For example, in chemistry, it was given to a team who developed systems that can predict the 3D structure of proteins, which is very linked to the functional properties of proteins. And this is something that is both extremely important to understand the fundamentals of the living, but also in terms of application, it's extremely important to develop new medicine. And this particular problem of protein design had been resisting scientists for several decades. It was really a major, major challenge. And suddenly with AI, it makes a major leap, which is right now changing a lot of things. And it's not only, for example, in chemistry or physics, it is profoundly changing fields that many people thought even 2 or 3 years ago were remote from any impact from AI, like mathematics. If you check today the way the best mathematicians in the world work, a number of them are now working like every day discussing with AI, trying to formalize their intuitions, to push their intuition and ask the AI to check whether there might be mistakes, maybe to propose even sometimes ideas. And you can follow, for example, Terence Tao, who is one of the greatest minds of our time, and he's been recently making some discoveries as a result of discussing with AI. It's the same in material design, for example, and I could go on forever. And so what it means also here is that I was saying that in school, children are taught the same disciplinary things than 50 years ago, and basically the way physics is taught at school now is the same it was taught more or less 50 years ago. The way mathematics is taught is more or less the same. But the way those sciences work are completely changing right now, and so we need to understand how to change the teaching of those things. And of course, the revolution is on education too, because as I just said, kids starting from middle schools are now massively using Gen AI in a way that's often not very pedagogically very relevant. But what's more is that it's putting right on the table, very big, a question that has been there for a long time in the school, but that AI in a way enables to confront really at once. Kids for decades have been having difficulties understanding why they go at school. Why is this that we are taught this stuff, that I don't see any link with the real life? And many of them have been like dropping from schools because of this lack of understanding and meaning and purpose. And now that there is a technology that's at the tip of their finger on their phone can basically answer all the exercises they are taught to learn at school, they say, but what is the purpose of me learning the mathematical technique A or B while I have a machine that can do it in a few seconds? And that's a very good question for them. And I think that this leads us to realize that as a collective, probably we did not spend enough time to explain to kids what the purpose is of school, why are they going to school. And in particular, for example, I think it's very important to realize that we've not explained to kids that when, for example, they are in mathematics and they are being taught this technique or this technique, what's important is not so much that at the end they know this technique or this technique. It is the learning path they've been going through. And why it's important is that they live in a changing world, as I was saying, and they will need to learn all their life. And learning is hard. Learning has to be learned itself. And one of the fundamental purposes of school is to learn how to learn. And then there are contexts that are taken, mathematics or physics or whatever, in which there are topics who are worked, which probably will not have any concrete impact in their real life, but they are an opportunity to train one's brain to learn and to discover new things. I'm not sure so many teachers have explained that to children. And there is also another reason, is that simply that among the basic needs of humans, there is the need to learn, and that is what I've been calling curiosity. So that's the headline of a French magazine, and it means why learn, and the subtitle is Curiosity, an Engine of Existence. And so it's also something that kids have not really been put in school in a context where they understand that it's an environment where one of the basic fulfillment they need to do, which is basically enabling their brain to flourish, can happen. And this is a problem. But not all kids are like this, actually. If you look kids from countries which do not have an education system, which are very poor, which need to struggle to go out of the poverty, actually in those countries, you see kids having a very, very different perspective with learning and very, very different perspective with school and with Gen AI. In many of those countries, kids are taking those opportunities and Gen AI, for example, as a way to discover and learn about the world, and that's really for them something extraordinary. And they have a very different relationship with those technologies. And so there are things that are also very positive. Okay, so how do we educate the children in this changing world? As I was saying, I think that basically it means that we need to put much more focus on learning how to learn. And one of the very important components of that is to do that leveraging one of the basic needs of the brain, curiosity, and its associated cognitive skills related to what one calls critical mind or metacognition. Okay, but so how do we do that? So first of all, it's useful to make more experimental studies to see, for example, links between things like curiosity and school and career achievement. There have been for so many years results correlating higher curiosity to great achievement. But the real question is, what are the mechanisms of curiosity? If we want to put back curiosity in the classroom, first, before working on interventions, we need to develop fundamental understanding. And it happens that trying to develop fundamental understanding of curiosity has been the activity of my lab for now a little bit more than 2 decades. And the way we came to studying curiosity is actually not at all from the perspective of education. It was from a kind of a fundamental question, which was trying to understand what are the mechanisms that enable human infants, but also the animals to go through open-ended development, how they can acquire such a diversity of skills in such a complicated world, in such a complicated body that they don't know at the start when they are born to the world, and under very limited resources of time and energy. You know, kids are not like an AI which lives in supercomputer, which can generate in parallel millions of worlds in which you can learn extremely with major data. They are in one world and in one body, and to learn they need to collect data with their body, which takes time and energy. And yet, in spite of these obstacles, they learn so many things so fast. So what are the forces that drive this? There are multiple forces that are important. Some forces are external, for example, social learning and imitation. But if you look at the way children learn, it cannot all be explained by this. There are also forces that are internal. And among those forces, there are forces that lead spontaneous exploration, all kinds of spontaneous exploration at all kinds of time scales. And this is basically what many people have called curiosity. Curiosity is an everyday word that intuitively relates to various forms of spontaneous exploration. And thus, this has been our purpose, to try to understand those forms of spontaneous exploration mechanisms. And one of mechanism of curiosity that's of particular importance is what we call autotelic exploration, or autotelic curiosity, which is the ability of children to invent their own goals, their own problems, their own questions, their own games, and they do that all over the place during their learning. And this seems to be extremely important for their development. But the fundamental question is, how do they select those games, those goals they self-generate, those problems they self-generate, those questions they self-generate? How do they generate them in the first place? And beyond driving what's happening in the short time scale, like in the time scale of a few seconds or a few minutes, what is the consequence of unfolding curiosity over a long time scale? So these are really the questions we've been working on across the years. We've been working on them from multiple perspectives. So one perspective is trying to develop theoretical models to answer those questions with the aim to understand better human curiosity. Then we've been trying to actually transfer some of those insights into machines, for example, building curiosity-driven autotelic robots, or more recently, autotelic generative AI systems. I will talk slightly about robots today, but not about autotelic generative AI systems. That will be for another time. And then, after we understand better, we recently came, in the recent years, to ask ourselves whether we can transfer some of those insights in applications, and in particular in education. Okay, so scientists have been looking still for a pretty long amount of time on curiosity. In the last century, from the 50s and even before, you had people like Berline or White who really were convinced that there are spontaneous exploration behaviors in children that cannot be explained only by extrinsic motivations like finding food or finding social recognition or protecting your own body from danger. And they proposed the intuition that probably in the brain there are circuits who reward things like novelty or surprise or intermediate complexity. So there was a lot of nice ideas like this, but one difficulty is that those remain just words and it was pretty vague, and it did not go so far in terms of really understanding the mechanisms. Things began to change somewhat 20 years ago when a group of people in the world in various labs from various disciplines, psychology, neuroscience, AI, tried to really say, let's dig into the mechanisms of curiosity. We want to understand those mechanisms, those algorithms really that are playing in the brain. And the way to go forward in many of those labs, including mine, was to see the child a bit as a little scientist. That was a vision that Jean Piaget was already a little bit taking, trying to explore the world, to make good predictive models of the world, and to be able to control the world in a robust manner. And so it means that the way we see the child, when he's not searching for food, where he's not hungry, where he's not searching social recognition, when he's just free to play, the way he's exploring the world is through two loops. The first loop is at a point in time, they're going to make experiments about the world. So there are several kinds of experiments that they could do. The prediction experiment, for example, here they say, let's mix those chemicals and let's try to predict what's going to happen as a result. But they can also do goal achievement experiment, like they invent in their head a goal. For example, let's build a 2 meters tower with wooden blocks, and let's try to do that for the next few minutes. And this is this particular kind of exploration that I call autotelic exploration. So they choose an experiment, they try to make predictions about what's going to happen, or they try to decide what to do based on their internal world model. They do it, and then they compare what they observe with what they thought would happen. This provides error signals, which is the basic loop of learning. But then the question is, when they are free to explore, how do they choose those experiments? And this is the loop we've been studying. That's kind of a metacognitive loop, where basically we're trying to understand mechanisms in the brain that monitor various aspects of the learning dynamics that's happening into the lower learning loops, measuring things like novelty or uncertainty, leading to what's called a measure of interestingness, typically in the brain, literally a neural circuit triggering dopamine and leading and driving the selection of the next experiments. And so we basically one of the main questions we've been looking at is how this top loop is working. So one of the questions to look at is what are the intrinsic rewards, the measures of interestingness that the brain is using. So there are many ideas or hypotheses that have been proposed in the literature. For example, some people said, well, the brain likes to explore situations or problems that are goals that lead to high uncertainty or high prediction errors or high surprise. There are many other ideas. So how do you test for those ideas? There are many ways you can test that. One way is kind of a theoretical / experimental way of testing them is that, okay, let's try to build a machine like a robot that we put in an environment that looks like the environment that an infant encounters. Like he comes to the world with a body he doesn't know. He's perceiving the world around, which is a complex environment. And he needs to be equipped with a mechanism to decide how to explore, to collect data, to be able to learn, to predict and control what's happening. And then the question is, if you want to drive exploration in this kind of robot, which mechanisms will enable that robots to actually learn efficiently about the world? Well, if you put, for example, mechanisms telling these robots focus on situations or goals where you have maximal prediction errors or maximal uncertainty, they will do weird things. You will find, for example, your robot spending the whole day in front of the window doing funny dances like this. And the advantage with a robot, as opposed to a child, is that you can open the brain and you can see everything that's happening. And actually, the robot is doing exactly what you asked. He found a situation where by, for example, trying to predict or control the colors of the cars or the colors of the shirts of people outside of the car, every time he tried to do that, he's wrong in the prediction. And because you asked this robot to actually focus on situations where he's wrong in predictions, well, it will do that all the day. I mean, but he's not going to learn anything. And children don't explore in such stupid manners. They do something that's much more smart. So you need to think about other more complicated mechanisms. So one of the mechanisms that we've been proposing as an hypothesis of the way to organize exploration is the learning progress hypothesis. And it says that basically the brain is tracking the learning dynamics of various learning situations, of various goals. And what's interesting are situations or goals in which progress is being made. So what do I mean? So imagine, for example, that you have 4 situations, 4 problems, 4 goals. If you imagine that you explore each of those goals, one of them, for example, the blue one, initially is easy to predict or control, and it stays very easy if you invest time in it. 3 others are very difficult in the start, but if you invest time and energy in them, you will progress in various ways. For example, the red one keeps very difficult. Maybe it's the same thing as trying to predict the colors of the cards outside of the window. But 2 others, you can learn about them. And you can learn at various rates. And this is the derivative of this curve, so the rate of learning, that's going to be used by the brain as a reward for deciding what's interesting to explore. And so in the world, of course, an individual does not know in advance the shape of those learning curves. So initially, for example, imagine that he has 4 opportunities to sample and to choose from. It needs to sample a little bit of them before having an idea of how much progress it's making. And so initially, we explore a bit everything and then discover that here there is one task that provides more learning progress and focus more often on it. Another one that's also providing learning progress, but a little bit less at the start, so focus on it, but a little bit less. And then the other one, which are either too easy or too difficult, he forgets them most of the time. Not totally, because maybe later on they become sources of learning progress. And then when the black one becomes to be completely learned, then it's not interesting anymore, and it shifts automatically to the other one. So that's a theoretical idea. The first thing we can do to play with this theoretical idea is, okay, let's build those robots with those machines. And so this is what we've been doing for a number of years in the past. And so here, for example, you see a machine that's equipped with basic motor primitives to move its body, with basic sensory primitives to perceive and locate objects in the environment, with learning tools, like, for example, when it's making experiments, he can make some statistics to build an internal model of the world. And then he's equipped with curiosity systems that enable it to sample goals. And goals here are basically imagine trajectories of objects in the environment and to track the learning dynamics of itself. So that's a metacognitive process. And then an action selection system that leads it to actually select the goals that provide maximal learning progress. At the start, basically it doesn't know anything about the world, and so it doesn't know where it can make learning progress. So he samples a little bit of everything, but he discovers that where there is most learning progress is actually moving an object that's called the hand for us. He doesn't know the hand initially is something that's spatially different from other objects. So he's focusing on moving the hand, and as a side effect, he's discovering that it can actually be used to push one of those little red objects in the front. And so now they become a niche of learning progress. He focuses on setting goals about them. And then progressively discover that one of them does not lead to anything special, but the other one actually triggers movements of this electric toy in front of it. And now the electric toy becomes an object of learning progress, and then progressively and so on, he discovers that he can actually learn to use the electric toy to move the ball in various directions. And so here actually we can discover that this robot finds its way to learn extremely efficiently in this complicated environment. And by the way, there are other things in the environment that he might consider as trying to learn. For example, pushing this object, or even pushing this one. He might, we know what it is, but actually he will discover that he cannot make any learning progress. Here it's because it's physically too far away for him to reach, but initially he doesn't know, so he tries to do things about those things. And there are also other things in the environment that are moving and that are unlearnable, and he learns to stop focusing on them. So that's the first good sign. It's working very well in robotic experiment. By the way, it's also very good for engineering this kind of mechanisms, because if you want to build a robot that learns, for example, how to move the ball in various directions, if you take the classical engineering approach, you focus only on this objective and you use an optimization method, the best one in the world, it will never work here because it's a problem with what's called rare rewards, which means that most of optimization methods, they are good to refine a method that's already working a little bit. When there is no an exemplar of a method that works at least a little bit, those methods, they just explore randomly. And if you explore randomly here, the probability that by chance you find a movement that moves the ball away is close to zero, and you need to wait millions of years. And that's the reason why in the last 6 to 7 years, the machine learning community, for example, Google DeepMind, who was using video games as a benchmark to test deep reinforcement learning systems, they made at the start a lot of progress, but quickly they were stopped by a number of games which were unsolvable. And they were unsolvable because there were problems with rare rewards like this one. And the only way they could solve those problems is actually by introducing this kind of curiosity mechanisms. And now in machine learning, curiosity mechanisms are everywhere in algorithms. It's become very common as a way to solve engineering problems. Okay, but let's come back to humans. So learning hypothesis. The learning progress hypothesis, we get good idea that in principle it might work to lead learning in real world environments, but can we test some of its prediction back with human experiments? So one such experiment was actually the work by Alexander Ten, who is around in the room, I don't know where, who was one of my previous PhD students, co-supervised with Jacqueline Gottlieb. And what Alex did is devise an experimental paradigm where there were several learning situations, little games. It was about monsters, and one had to try to guess what they preferred to eat. And basically, human subjects were put in a situation where they were told, you have 30 minutes in front of you, and here are 4 games. You can explore them the way you want, and then at the end, we won't test you, we won't compare you to others, so they were really free to explore. And then with some mathematical techniques, we try to look at the data of their exploration trajectories and to infer what are the utility functions that they might be using and that best explain their behavior. And so basically, what are the intrinsic rewards they choose to decide what's interesting to explore. And so, for example, we consider the space of many such utility functions, some of them using prediction errors, some of them using learning progress, some of them combining various measures, including learning progress. And interestingly, it happened that the models that explain best the exploration behavior of the population are models that include a learning progress component, combined with prediction errors, in actually relatively complex manners and in a way that is dependent on each particular person, which means that, for example, utility function can have a weight, and while the structure that explains best everyone is a structure that is common and mixing those components, the particular weights of those components differ from individual to individual. And interestingly, beyond this confirmation of the use of the monitoring of learning progress to drive exploration, other labs in the world in parallel develop experimental paradigms to test the same learning progress hypothesis. For example, the team around Francesco Poli, who did very similar experiments with 8-month-old infants. For example, here showing that looking time and engagement correlates with learning progress, but not with surprise and not with prediction errors. He's been doing experiments with 4-year-olds, showing that exploration decisions depend on learning progress combined with novelty, very similar to what Alex found. He's been doing experiments with adults, showing that where adults explore next correlates with expected learning progress and novelty also. Some other labs, for example, found that engagement and flow experience correlates with learning progress. Or recently, you have also the team around Julia Leonard, who did experiments with physical toys in which she could manipulate very precisely the learning progress. And she showed that children who were given evidence of their learning progress persist more on challenging tasks, and this is independent of the final percentage of success in those tasks, showing really the importance of learning progress to motivate exploration. Okay. Let's move on to the follow-up question. Okay, it seems that learning progress is important, and we observe in humans experiments of all ages that it's used by the brain to decide what to do next in setups that concern time spans of a few minutes or a few dozen minutes. But what happens if you kind of imagine that those mechanisms organize exploration for a very long amount of time? And so this is what we've been exploring with computer simulations, for example, simulating the development of speech sounds. And the kind of things we do is that we build an artificial human with a model of the vocal tract, a model of the auditory system, and then we let the kind of curiosity mechanisms I presented lead the exploration of the vocal tract, of the sound it can produce. And we put actually this individual in an environment with speech sounds that share the same structural properties that existing speech sounds of human languages. And then we observe what's happening. And what we observe is the progressive self-organization of developmental stages of increasing complexity, both in terms, for example, for going from no phonation to unarticulated phonation to canonical babbling, and then moving from vocal exploration that is not influenced by the social environments to a shift to imitation. And the shift to imitation, for example, here is explained by the fact that early on, the individual has not sufficient skills to master the vocal tract to make any progress in imitating the sounds in the environment. It's only later on, when it has acquired the skills, that now it can detect, it can make progress, that imitation becomes interesting and motivating. And that's intriguing because those self-organized trajectories, they have the same regularities and the same diversity properties than the one we observe across the world in developing children. I'm going to go fast, but we've been observing similar structures in tool use development, for example. But let's move to the next stage of my presentation. So now that we've learned a little bit of new things about curiosity, can we leverage some of them to understand how we could stimulate learning at school that's more motivating or more driven by curiosity? So we've done several projects about that. One first project that was led by Benjamin Clément, who is also in the room, a previous PhD with me, was the idea, okay, so now we understand that when children do activities where there is maximal learning progress, we know that it's both extremely efficient for learning, for theoretical reasons, and we also know that it's a strong factor for motivating them. Then one of the difficulties in a classroom is that in general, the teacher is in front of many students, and for simple practical reason, it's difficult even for the best teachers in the world to propose a particular sequence of explanations and exercises to each particular child. And thus it means that many of those children, they will get at some point in time explanation and exercises that are not well fitted to their current skills and to what would lead them to maximal learning progress. So also, I said earlier that it's kind of a basic property of the brain to be spontaneously motivated by this kind of curiosity. And so you might say, but why won't we actually let the children in the school choose by themselves the learning material they should do at some point? So it seems to be like a priori a good idea, since the brain is wired to explore driven by this kind of curiosity. But there is a problem. The problem is that the curiosity loop I just described to you relies on metacognitive skills. For example, the ability to identify where one is having high competence or low competence, high learning progress or low learning progress. And metacognition is something that develops very slowly in children, which means that they might actually, a number of them, make mistakes in terms of they might believe that here they make progress, but they are not so much making progress, and here it's the contrary. And so one first approach to deal with that is to devise, for example, educational software that might actually support some of those metacognitive limitations and do the calculation for them and try to identify exercises that maximize their learning progress. And so Benjamin actually worked on an AI method that starts from a graph of exercises that's actually designed by a pedagogical expert in a given domain, so for example in mathematics, and that's going to move the child in sub-areas of those graphs in a way that's going to maximize the learning progress. And so we did first experiments in primary schools, and we tried to compare such an approach with an educational technology where the sequence of exercises was designed by an expert in the didactics of mathematics, trying to use the best knowledge that he has. And we measured several things. First, we measured the impact on learning, both during the path of interacting with the educational technologies, but also comparing results of a pre-test and a post-test on a different medium. And we observed indeed that the personalization using learning progress manages to get a higher diversity of children further in their skills. There are actually 4 cases here. I'm going to say explain this in 1 second. But the second thing that we measured is motivational impact, and we use various tools from psychology to measure dimensions of their motivation. And we also could observe that the personalized trajectory based on maximizing learning progress leads children to be more motivated than the one who have to go through a handmade trajectory. And so now, why are there 4 things and not those 2 things? It's because at some point we realize that that's nice from us to try to identify in the place of children where they do learning progress and propose them those exercises, but in a way that's a little bit contradictory to the basic theoretical idea of curiosity-driven learning, because that curiosity-driven learning is basically about choosing for oneself what one is going to learn. And so here we were removing fully the agency of children. And so that was kind of a dissonance. And so what we tried to do is something that's kind of hybrid. We decided to introduce back into the system choices that children could make to reintroduce some form of agency. And the choices that we proposed to them were kind of orthogonal to choosing the difficulty of exercises, like for example choices about the cosmetics of what's happening. And what we observed was quite interesting. What we observed is that introducing the choices on top of the curricula that are personalized with the algorithms boosted both their learning efficiency and their motivation. All fine. But then when we introduced choices on top of the hand-defined learning trajectories, what we observe is that motivation were a little bit higher, all fine, but learning efficiency was lower. And it seemed to be quite strange in a way, but after thinking about that, I think we understood what's happening is that the handmade trajectory was very frustrating for many kids. Like at some points for some kids it was too slow, for other kids it was too fast, and that was really frustrating. And at some point, then they get an opportunity to gamify the thing and to say, oh, maybe I want to make an exercises about the pink bear here, and this suddenly is an escape way for themselves from this frustrating and boring system. So what it means is that here we see an example where gamification and agentification is working when the personalization is well done, but is counterproductive if actually the learning pathway is not so adapted to them. So beware introducing gamification. And then, interestingly, because we had those very encouraging results, we started working with a number of actors in the edtech industry and also with the Ministry of Education that later on enabled those basic principles to be actually transferred is in several large-scale educational technologies, for example, for teaching math or languages in primary schools or in high schools, and that are right now actually deployed at the national level. But let me move on. Can I have an idea of the time and when I should really stop?
5 to 10 minutes.
Okay, 5-10 minutes is when I should really stop, or when including the questions?
Questions and plus questions.
Okay.
20 minutes.
Okay, good. Thank you very much. Okay, so here basically we had an approach that kind of tried to put children in learning situations where they could experience learning progress, and thus, for example, leading them to do math in a way that's leveraging a little bit the curiosity circuits. But now, maybe a further question is it possible to train curiosity itself? Curiosity has many facets, as we've been saying, so maybe let's focus on some facets. One facet of curiosity is the ability to ask questions, to ask curious questions, to ask divergent questions. So can we train this? So before I actually go on the training, I'd like to present one study we did recently, and that's about the question, do children know how to ask good questions to generative AI like ChatGPT? That links to what I was saying at the start of my presentation. Okay, it's a reality. Kids use ChatGPT very often. They do that in an educational context. So instead of telling them don't use it, let's try to understand how they use it and later on to nudge them into using it in the right way. And so the first step is understanding how they use it, how they understand it, and in particular, do they know how to ask questions to it? And we did an experiment that was led by another of previous PhD students in the room today, Rania Abdelghani. And what she did is that she designed an experiment that was about little science inquiry exercises, typically the kind of exercise that a teacher might give to pupils when they go at home. And those exercises are like this one on the left. You give them a little sheet of paper. Anna wants to understand the properties of light. She started with a simple test by dropping a pencil into a glass of water. Here is what she saw. Your aim is to understand why the pencil looks different. And then the pupils, they were given access to ChatGPT, and then they went to a structured interaction. And the first step of the interaction was that they were given a prompt that they might ask to ChatGPT, and they were asked, do you think that's a good prompt or that's a bad prompt, given the exercise you have? And on purpose, we designed some prompts that are relatively adequate for solving the exercise, and some other prompts which are not adequate. For example, they lack sufficient context. Remember that the kids, they get the exercise on a sheet of paper and ChatGPT is on their screen. And so, for example, an example of an adequate prompt here is what light property makes a pencil change direction when dropped into a glass of water? Good. And an inadequate prompt is why is the pencil different? And here, of course, ChatGPT cannot get the right context because he cannot see the picture the child is looking. So for us, obviously it seems to be a wrong prompt. Is it the case for children? So then after they were given those two prompts, they were said, they could say, well, that's a good, that's a bad prompt. They were said, okay, if you want, you can reuse that prompt and ask it to ChatGPT, but if you don't want, you can ask your own prompts, your own questions. Then they go to the question, they get an answer of ChatGPT, and then they ask, what do you think about the answer? Do you think it's good? Do you think it enables to address the question, or do you think it's not satisfying? If it's not satisfying, if you want, you can ask another question. And so we went to middle schools. So I have to say that's a kind of a small scale study. That's more of a pilot study. We aim to scale it more in the future, but that's already very interesting what we observe. So the first thing, that the population we were working with, again, the vast majority said they had already used ChatGPT. First observation, the average success rate in solving those exercises, each of them had 6 exercises, is 50%. So it means that those science exercises, which are not foolishly complicated, by the way, some kids get near everything right, so it's completely possible to get it right, but the average mark is like 50% right. So it's really not high, given that they have full access to ChatGPT. Then we looked at the way they can differentiate good and bad questions. And the graph, for example, on the left, basically shows that there is a large proportion of children who basically don't know how to differentiate good for bad prompt. They answer more or less randomly. The one here, they have a tendency to say that a bad prompt is good and a good prompt is bad. And the other one here do a little bit better. And then we observe the same actually for the capacity to differentiate between the good and the bad answers. In average, they are not so good at that. They really struggle at this. And so what we try to understand is whether there are factors that modulate those results. And there are actually some factors. Again, please take that with a grain of salt because that's a kind of a preliminary study, but still that's interesting. So first of all, we had them answer a questionnaire for self-evaluation of metacognitive skills. And what we observe is that those skills who rate higher on metacognitive skills, they do actually have better results in this experiment. Another thing that we measured is various aspects of their familiarity and proficiency, or self-declared proficiency, that's an important difference, with generative AI and ChatGPT. And what we observe is that the more kids tend to say they know ChatGPT, its limits, etc., the less good are the results in the experiment. This actually you can understand relatively well in the sense that most of these kids, probably they came to discover ChatGPT on their own, building their own mental metaphors to try to understand it, and at the same time hearing every day in the media that superintelligence is coming the next day and will be better than the best scientists of the world. And they are overconfident. And I mean, that's not so surprising. But so, conclusion, if we want to address that, we want to train them with more AI literacy, and we need to train their metacognitive skills. Okay, and so let me finish the presentation where with the question, okay, so now can we really train their question-asking skills, and in particular their curious or divergent question-asking skills? And so here is another study that was also led by Rania, where we were wondering whether very simple exercises could get the skills to develop their ability to ask divergent questions. And so here what we did is that we designed a little conversational agent, and it gets an activity where we present a text on, for example, about dinosaurs or volcanoes to primary school children, and then we gave cues to get them produce questions that are about the topic of the text, but where the answer is not in the text. This is what we are calling basically divergent questions. And so we compared different approaches, different kinds of cues to see whether it can enable them to progress in their ways to ask divergent questions. We compared diverse kinds of cues in the same environment to be able to compare things that are comparable. So one kind of cues we tried, for example, was simple syntactic cues, like maybe you could ask a question that starts with by what, or by why, or by how, or whatever. And then we compared some approaches where we gave them also semantic cues, for example, giving them a keyword that is associated to the text, but in a loose manner. So I won't enter into the details, but just very, very quickly, what we observe is that it is actually possible by various kinds of interaction to actually improve the way they ask questions, both at the syntactic level, but also at the semantic level, being more divergent. And what we observe is that doing the training that work best in getting them ask better questions, after the training, we get them into a space where they are free to explore new pedagogical materials, and we want to measure how much they explore this space, and we see that having been trained to ask questions leads them to explore further in that space, and also to remember better the information they have been acquiring. But something that in that experiment we did not manage to change was the negative a priori perception that the majority of kids have about curiosity. For many reasons, many of them, they believe asking a curious question in the context of this classroom is bad. They could think this, it's bad because maybe their friends will say, oh, you want to show off yourself. Maybe they think it's bad because they think that if they ask a question, maybe the teacher will think that they are bad and they have not worked enough. So many reasons. And here we did not change their perception. And so it's only with a more recent, fuller intervention where we complemented procedural training that's related to various metacognitive skills to curious question asking. We complemented that also with the declarative training where we had really a series of very short videos explaining them what's curiosity, what's metacognition, how does it work, what's the importance in learning, why is it important to be curious in the classroom, etc., etc. That finally we started to have an effect in changing their perception of curiosity. Okay, so sorry for being very fast, but I need to stop here. And just while I'm stopping, it's the 1 minute of publicity. And call for help. With two amazing people, Didier Roy and Clémentine Latron, we wrote a book called in French, C'est pas moi, c'est l'IA, it's not me, it's AI. That's about trying to develop the AI literacy of children. It covers everything, the mechanisms, the societal stakes from education, democracy, industry, etc. And we are looking into trying to find editors in other countries so that not only the French kids can benefit from it, but kids speaking other languages. And if some of you know connections in Germany, I'm happy to discuss. Thank you.